Hey y'all, welcome back to another round of Robinson Rants. And yeah, three more example problems for you, and we'll take them one at a time. So, first question ahead of you here, we've got an interesting circuit design, and we're interested in finding V naught as a function of t that is the drop across the capacitor as a function of time. And one of the things I will warn you about before I set you loose to try it on your own is be wary of this structure right here. Okay? You'll find that that structure in particular can be simplified with a little bit of ingenuity. So go ahead, take a minute, see if you can hack out the answer. You got it? Good, 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 good. So let me first look at this structure, the one that I pointed out to you. And the reason I highlighted it is because when I was working the example problem, that can get kind of arduous, if you will. So if I focus in on that for a second, you realize that you can actually redraw it slightly differently. And so I'll go ahead and draw it. I'm going to keep the 300 ohm resistor as is. And I'm going to shrink the connections between the 100 ohm resistors. So I'm going to end up going like this. And hopefully, 100 and 100, hopefully you see all of a sudden that this is a delta connection. And we can use that, this is a delta connection, we can use that and turn it into a T connection. I think I hinted at this at one of your labs for the equivalent resistances. I think it was about lab 5 or so, that sometimes when you run into this structure, it's easier to convert it into a different structure, what's called a T, or sometimes you'll see it as a Y, a T or a Y. Okay. And that sometimes makes it easier to perform subsequent analysis. If you consider these three connections, I'll call it little a, little b, and little c, okay? Those are the same connections here, A, B, and C. And we find that the resistor, this equivalent resistance that I've placed right here, okay, I'll call it R1, that R1 can be written as the two adjacent resistors to node this location C. So I'll put 100 squared divided by the sum of all three resistors. That's 500. And so we can do the same thing for resistor 2 and resistor 3. So resistor 2, I need to look at the two adjacent resistors in the delta and multiply those. So that's 300 times 100. Okay. And again, it's over the sum of all the resistors. And similarly for resistor 3, you see you do the same process, 300 times 100 and 500. So at the end of the day, what do we have? Let's see, we can cancel out a couple zeros. So we get 300 divided by 5, that's 60 ohms. Of course, this bottom one will give us 60 ohms as well. And this top one will give us 1/3, right? Instead of 300, I only have 100. So I end up with 20. Okay. So I would say rather than considering this circuit, we now can consider a circuit with an 80 ohm resistor connected to, now this is connection point little a, so we can think of that as being connected to a 60 ohm resistor. Going down, there's our T, so there's the 20. Here's the 60, oops, excuse me, 60. Going over to the inductor, okay, to our potential supply, and our capacitor. Okay. So go ahead. If you got stuck there, go ahead. Now see if you can analyze this equivalent resistance, or equivalent circuit. Excuse me, I lost my head there. Hey, you got it? Okay. Let's go ahead now and find the initial conditions before the switch is opened. Okay, so let's go ahead and find the two initial conditions for time less than 0. That is the moment before the switch is opened. And we know that before the switch is opened, the capacitor is fully charged, which means I can completely ignore the left side of this circuit. And so what I see is that I have 100 volts and applied to a 100 ohm resistor, right? I can follow that path. And so I get that the initial current flowing through that inductor is equal to, yeah, you see it, 1 amp. Okay. Well, if I know that there's 1 amp flowing through the circuit, I can now determine the value of the potential drop across the capacitor, or if you will, the potential drop between these two nodes, which I am labeling as A and B. We know it's a 100-volt jump across the potential supply. So I'll put 100. And then I have a 40 ohm resistor, which has 1 amp of current flowing through it. And so at the end of the day, I should see that the capacitor has 60 volts across it. That is the potential drop, the initial potential drop across the capacitor. Well, why stop there? Let's finish off and get the two other initial conditions when the switch is opened. So thinking of the initial conditions at, say, time just greater than 0. And this is where we relate the potential across the capacitor to that across the inductor, or the current flowing from the capacitor to the current from the inductor. So we need to open the switch to get that. I haven't emphasized that enough, I realized, as going back and reviewing the other videos. So we have to do some initial conditions right before the switch is opened and right after the switch is opened. So after the switch is opened, you'll notice, okay, all of a sudden we have this situation, this 140 connected to this 60, connected to the inductor, and back to the capacitor. Okay. Now the problem, I believe, we have that, yes, okay, so the problem tells us they want this side to be the high and the low side. Okay, well, at time greater than 0, we know that for that brief instant after the switch is opened, there still should be I naught of L flowing through here. And the only place for that current to come from, that charge that goes into that current, if you will, is from the capacitor. And so I get that for the initial current of the capacitor, that must be equal to this initial current from the inductor. Okay? And so remembering the relationships between the charge of the capacitor, the capacitance, and its potential drop, we take a time derivative. And don't forget, since the capacitor is serving as the source now, I'm going to pick up that extra negative sign. So I'm going to end up with the current coming from the capacitor divided by the capacitance is equal to the time derivative of the potential drop. And since I'm interested at that moment right after the switch is thrown, I can replace this time varying current with this initial current. So at the end of the day, I get that negative I naught L over C is equal to the change in the capacitor's potential per unit time at time equals 0. Well, why don't we go for broke? Let's find the fourth one, right? And that fourth one probably is slightly, well, I'd say slightly easier. We now know the potential drop across the capacitor. That's V naught C right here. Furthermore, we know the current, Furthermore, we know the current flowing through the resistors. It's the 1 amp. And so we have an idea about the drop across the inductor. Right? For lack of space, I guess if it's okay, we'll just put it right over here. Okay. So what do I have? I have the jump of V naught C minus the drops across these resistors. So I have V naught C minus 200 times my current. And whatever that is must equal the potential drop across the inductor. So I have my 60 volts minus 200. So at the end of the day, I should get something like negative 140 is the initial drop across the inductor. Well, that just equals the time derivative of the inductor current times L I'll leave it in terms of the number. Okay. And so we get that the change in IL at time equals 0 is equal to this negative 140 divided by the inductor value. Now, usually you don't have to get all four of those, right? Usually you're, for example, in this question, we're just asked about the inductor. So the inductor current and the change in the inductor current should be sufficient. I'm just doing all four for, I don't know, completeness. Okay? So now we're at a point where we are ready to find all the characteristics about the circuit. Okay? And this is where we can turn to our handy dandy table if you want. So what we have is our 500 microfarad capacitor discharging. Connected to that, we have a 200 ohm resistor connected to a 200 millihenry inductor. So what we have is an RLC series circuit. And now you can see where having that nice table will really help us out. Okay, you ready for it? Because we have an RLC circuit, that alpha value, the coefficient of the linear term in our quadratic formula, is going to be given by R over 2L. So we can go ahead and calculate that out. The 200 divided by 2 times 200. Okay. And we have that 10 to the third millihenries to the third. So I'll put that in the numerator. Well, that's easy enough. This gives us a value of 500. And the astute observer will notice this should be something like radians per second. Well, that's the first one. Omega naught, which is given by 1 over the square root of LC. Okay. that is going to be equal to 1, and we have 500 times 200. Well, that seems kind of nice. So 500 times 200. And then we have 10 to the negative 9th. And we'll take the square root there. Well, that at the end of the day, we can cancel out 4 of these zeros. 1, 2, 3, 4. And the 5th zero because 5 times 2. So we get 1 over 10 to the negative 4th square rooted. And we get 100. Again, radians per second. And so now we do the comparison between the two, right? We compare alpha to omega. And we see that because alpha is greater than omega, or if you prefer, what we're really thinking about is this r over 2l squared minus 1 over LC square rooted. That's really what we're thinking about here. Since we see that this term is greater than that term, we have an overdamped circuit. So we are now in the position where we can go ahead and apply some of our other ideas. First of all, let's go ahead and get a value for what I call r plus and minus. And here's where it's nice to have already had alpha calculated. You have negative 500 plus or minus the square root of 500 squared minus 100 squared. Yeah, squared. Okay. Square rooted. So at the end of the day, we have something that says negative 500 plus or minus. This is going to be ugly. So it's 25 minus 1. So it's 100 times the square root of 24. So I guess, let's see, you can pull out a common factor of 4. So I guess you'll get 200 times the square root of 6. I'll leave it in terms of r plus or minus, but now we have that value. Okay? Well, what else do we need? We need to go ahead and find, we know what the form of the equation is. We still need to go ahead and find the initial conditions. And again, this is where our handy dandy table comes into play. So let's decide. Let's go ahead and find the current, I. We're interested in finding the potential drop across the inductor. Let's just go ahead and find the current through the inductor. Okay. Well, we know that I naught from our handy dandy table should be I at infinity. So the terminal behavior plus our coefficient A plus our coefficient B. And looking back, this is a series RLC circuit, and there are no supplies, right? No currents, no potentials. Okay. Meaning that eventually all the current's going to bleed out. It's going to go away. All of the energy will be dissipated by the resistors in the circuit. And so the terminal behavior, the amount of current flowing as time goes to infinity, will equal 0. And we already know the initial. So we can plug in our values. We'll have something like 1 is equal to 0 plus A plus B. So there's one equation that we need. The second equation, again from our handy dandy charts, is looking at what the derivative of I is doing at time equals 0. And we can set that equal to A times our R plus value plus B times our R minus value. Right? right? Keeping in mind those are from the previous page. And so we decided originally that the change in the current was negative 140 divided by L. We have that negative 140 divided by L, 200, and then we have the milli, so I'll put the 10 to the third. Okay, that's what we said I dot was. So we can plug that in, right? So we have 140 divided by 200 times 10 to the third. Guess I'll put the negative sign in there. Equals AR plus B R minus. I don't know. You want to go ahead and solve it? Okay. Yeah, go for it. So this is 7/10. So this is what, negative 700 equals A times negative 10.1 plus B times negative 989.9. At least the negative signs cancel out. Oh yeah, you could just use your matrices if you want, right? This is a system of equations. So you could, and they're linear, so you could go ahead and solve this for A and B. Okay. So I get something rather small. A is equal to 0.30 and B is equal to 0.70. I'm rounding, of course, but we're done. Right? Believe it or not, we've solved the whole problem. You want me to write the final solution? Oh, okay. Yeah, let's go ahead and write the final solution. So what we have is that the capacitor or the inductor current as a function of time is equal to 0.30, my A value, e to the r plus, so I have negative 10.1 t, okay, plus b, which is the 0.7, e to the negative 989.9. Ta-da! Notice we didn't have to touch the differential equations at all or anything. That's just because we identified what kind of circuit we were dealing with, and so then we can use those generalized results. A lot faster, huh? Okay, let's do another one. Okay, go. Take a minute, see if you can hack this one out. You got it? Yeah, good. And we're looking for that VC of T, the potential drop across the capacitor. Well, let's do the same song and dance. We have to analyze the circuit before the switch is thrown. So we have something like our potential supply connected to 12 ohms, the 100 millihenry circuit, our 2 millifarad, our 18 ohm resistor. So here's our initial system. Of course, we realize that the capacitor is fully charged, so we can pretend that that's not even there. And so we see that the initial current flowing through our inductor, is that 150 divided by 30. 150 volt supply divided by the 30 ohm resistance. And so we get 5 amps. Keeping in mind it's going from right to left. Well, what does that mean about the drop across the capacitor? Well, if there's 5 amps flowing through this 18 ohm resistor, that means the initial drop across the capacitor must be 5 times 18, or 90 volts. Keeping in mind, and I'll label it, this is the high side, that's the low side. Well, how about after the switch is opened? These are two of the initial conditions, depending on what we're interested in finding. How about after the switch is opened? There I have a situation. So notice I now change my supply to 60 instead of 100. And there I have a situation where I'm now connected to a 10 ohm resistor. I've changed from 4 to 2. I have a 10 ohm resistor. Still have the 100 millihenry. Okay. I still have this capacitor now. There we go. And I have this resistor. Oh, excuse me. I forgot. At the time that it's opened, we disconnect that resistor as well. Okay. So here's what I'm dealing with. Uh-oh. That looks like an RLC series circuit to me. Okay. So and again, that dictates that our alpha is given by R over 2L. Okay. Good. Okay, well, we better find the changing current and the changing voltage. It's just helpful to have. And for good practice, I think it's good to just do all four of them. Okay. Well, here, what we have, we know that this is plus minus V naught C. Okay. So let's go ahead and get at I dot for a moment. The potential drop across the inductor, well, first of all, remember we're going this way with our current. Oh, excuse me. They tell us the low and the high sides for the capacitor as well. So they said this is the low side, that's the high side. So I'm going to put a negative sign in there, the negative 90. Okay. And that just makes sure that that accounts for the fact that what they label as the low side is actually the high side. Okay, so in any case, so what do I have here? I have the low side and the high side. So as I walk around, I have a drop of negative 60 plus, because I have a jump per my labeling. Okay. And then that's one side. And then I also have this drop of the 10 ohms times the current. Call it I naught L. Okay. And that equals the potential difference across my inductor. Okay. Of course, this is high and that's low. And so we have a way of relating that. We plug in all of our values. We get negative 60 minus the 90 minus the 10 times the 5. And that's the potential drop across VL. So we get something like negative 200. And of course, that's equal to Li dot at time equals 0. And so we're golden, right? Oh, it's 100 millihenries. So 200 divided by 100 gives me 2,000. I get something like negative 2,000 equals I dot at time equals 0. Well, how about V dot? How quickly is the charge on the capacitor changing? And that will relate to V dot. And okay, well, I'm out of space. I guess I'll have to redraw it. But the trick is, again, that we have that 5 amp current, right? That 5 amp current is coming from the capacitor. And so we have something that says, well, this would be Q over C again. So the changing voltage on the capacitor must be that negative 5, that I naught L, divided by the capacitance. Well, that's just equal to the negative 5 amps divided by, now I've already forgotten the capacitance, 2 millifarads. The 2 millifarads. So what do I get here? I get negative 2.5, yeah, 2,500. There is equal to the time derivative of the potential across the capacitor at time equals 0. Okay. Good. Well, now we are in a situation where we need to decide what's the behavior of our circuit. And so we need to look at alpha, which is R over 2L. Well, our R is 10. 2 times 100 millihenries. So I get 10 to the third up here. Okay. So I have 100 divided by 2, right? 10,000 divided by 100 gives me 100. So this gives me an alpha value of 50. And again, that's radians per second. Well, how about omega naught, which is defined as 1 over LC square rooted? Okay. Well, that's going to be equal to 1 over, we have the 100 millihenries, excuse me, 10 to the negative third. And our capacitor value is 2 millifarads. So I have another 2 times 10 to the negative third and square rooted. Okay. So what do I have at the end of the day here? I have something like 10 to the third divided by the square root of 200. Right? Oh, I guess I could put this as, so this is something like 10 to the second divided by the square root of 2. Okay. 100 divided by the square root of 2. Okay. Which means, yeah, you see it, right? Since the square root of 2 is less than 2, then 100 divided by the square root of 2 will be greater than 100 divided by 2. So we're dealing with an underdamped situation. So we know that the form of the potential as a function of time is going to be something like a sine of omega d, excuse me, cosine omega dt plus this b sine of omega d times t with some extra stuff, e to the negative alpha t. Ready for it? Let's go. So, well, I should probably determine my value for omega d. So let's go ahead and do that. Omega d is defined as omega naught squared minus alpha squared square rooted. Okay. And so for omega d, I had 100 over the square root of 2 minus 100 over 2. And we need to square both of those values. And so what we get at the end of the day is 100 times 1 over 2 minus 1 over 4. Okay. Not to worry, of course this is 1/2. Not to worry, that is equal to 100 times the square root of 1/4. And so we can say that omega d is equal to 50. And again, that would be radians per second. So what we're left to do now is determine the constants A and B based on the initial conditions. So we go to our handy dandy table again, and we see that, okay, well, if I'm interested in the potential drop across the capacitor, I have to look at the terminal behavior. So I'll say the potential drop at infinity, and that plus B, plus A. Okay. The coefficient of the cosine term. Okay. Well, I've already got the initial drop at time equals 0. That was negative 90. And we look at our circuit, and we see that as time goes to infinity, the potential should be not a negative 90, but a positive 60. So we put 60, let's say. And so we see that our A value must be a negative 150. So there's one of them, if I could actually circle it. The other thing that we need to look at was the time varying behavior of the capacitor at time equals 0. And for that, again, our handy dandy chart tells us that we should have something that says negative alpha times A plus omega D times B. And so we find our time change. We said that this was a negative 2500. We have alpha, which is a negative 50. A is negative 150. Omega is 50. And we have our B. Got it? Okay, and of course you see we have the 2500. Now we have 5 times 15, which is 75. Double negative sign, so we get minus 7500 here equals 50B. So 10,000 divided by 50, that should be 200 equals B. Don't forget the negative sign. And we're done, believe it or not, right? We can now write out our solution for the potential drop across the capacitor. It is equal to negative 150 cosine of 50t minus 200 sine of 50t times, we have that e to the negative 50, right? That's the alpha term, times t. And we have to add in our terminal behavior, right, as time goes to infinity. And that's just to make sure, right, as this first term that I've written down gets wiped out, and so you have this plus 60 left behind. There we go. Whole lot faster, isn't it? Once you kind of understand where those equations came from, it's a whole lot easier just to use them. There we go. Pretty cool, huh? Well, let's go for one more. Oh, Greg, no, not another one. Yes, another one. Let's do one more. Okay, go ahead, solve this one. You got it? Yeah, good. Okay, let's go at it. So at time equals 0, we close the switch. So before that, we have two situations, if you will. So there's our inductor, here's our capacitor. So this is initial, right? That other half of the circuit is just not involved whatsoever. And furthermore, because the capacitor is fully charged, we can even wipe that out. So the initial current through the inductor is simply this 36 divided by 300. Right? The inductor acts like a wire. So what do we have at the end of the day? Well, this is, well, it's 12 divided by 30. Excuse me, not 12. It's 12 divided by 100. There we go. Right, take the common 3 out, and then, okay, yeah. Furthermore, you can tell me right away, what's the potential drop across the capacitor? Remember the wire, remember the inductor's a wire. Yeah, it's 0. Right, you've shorted out the capacitor. Yeah, which is pretty cool. Okay, well, how about when the moment the switch is closed? Now, the time when the switch is thrown, right, you can kind of, okay, so we connect right here. And what we need to find is at that time, what's the current going through the capacitor? That will help us determine the change in the capacitor's voltage at time equals 0. Well, okay. Well, momentarily, this loop right here, the current that's coming from the 36 volt supply should be going through the inductor. You could get that, for example, with node voltage, if we applied node voltage to the top. So what that we can think of is, say, let's see, we'll say that the two currents are going this way. And so we get the current flowing through the capacitor plus the current flowing through this 150 inductor, or excuse me, resistor. So okay, that should equal this 20 milliamps. Now you say, why did I say V naught C? Remember, the instant when this is closed, we have the potential difference across that resistor. It's equal to the capacitor. Of course, the capacitor is shorted out, so this sucker goes away. And so what we end up with is that the time varying potential at time equals 0 must be this 20 milliamps divided by the capacitance. Sweet. Well, how about the potential difference across the inductor? That's the other one that we need to find. The instant that the switch is closed. And we get, well, the instant that the switch is closed, the inductor and the capacitor are in parallel. And so it should be equal to V naught C, which is, of course, 0. That means that the time derivative of the current through the inductor at time equals 0 is also 0. So a brief instant after the switch is closed, the current doesn't change at all. So let's get at solving this circuit. Okay. Now you'll notice, of course, it's an RLC parallel. Well, and maybe one of the last things that will help us out is trying to figure out what the R is. Right? We need to think about that. And I think probably the best way to go at it is noticing that we have this 36 volt supply in series with this 300 ohm resistor connected to the rest of the circuit. You see where I'm going here? Yeah, let's turn this into, let's do a source transformation. So what we should end up with is a current supply of 0.12 amps connected in parallel with our 300 ohm resistor, which of course is in parallel with the 150 ohm resistor, and I forgot the 20 millihenry inductor and the capacitor. What is this? The 500 nanofarad? 20, 150, 50. Yeah. And we also have, excuse me, I've run out of space now. I'll put it over here. We also have the 20 milliamp supply. Well, that makes it easy, right? Let's go ahead. You have 1 over 300 plus 1 over 150 inverted. Okay. So this gives us 100, right? 1 plus 2 is 3, and then 300 divided by 3, so that'll give you 100. And over here, right, this is 100 milliamps going up. So we, at the end of the day, and maybe that would have been better to do before we did our initial and final analysis, but at the end of the day, we have something that says 100 omega to 20 millihenry and 500 nanofarad circuit. Cool, right? Well, let's go ahead and figure out what kind of circuit this is. Because we have an RLC parallel circuit, that means that our alpha is actually given by 2 over RC. And so we can see that's 1 over 200 times this 500, and I'll put the 10 to the 9th in the numerator. So 10 to the 9th divided by 10,000. So is this 10 to the 5th? 10 to, oh, excuse me, 100,000. So I'll say 10 to the 4th, right? 10 followed by 4 zeros. So 10 followed by 4 zeros is 100,000. Okay, there we go. So we have radians per second here. Well, let's go ahead and figure out what the natural frequency is, this 1 over LC. And again, let's see. We have 20 times 500, and this is over 10 to the milli and nano, so this would be 10 to the 12th. Right. So this is 10 to the 4th, so this should give me something like 10 to the 8th radians per second. Oh, I forgot the square root. Oh. Oh, yeah. Sweet factor. All right. You see it? I forgot the square root. 1 over LC is omega squared. Okay. Yeah. And you see it, right? Yeah, we have a critically damped. We have a critically damped oscillator. So let's go at it. I shouldn't say critically damped oscillator. That's contradictory. We have a critically damped circuit. Okay. Well, let's go at it then. We again pull out our handy dandy table. And for the critically damped circuit, again, what do we want to find here? Let's I. Okay, so let's do IL. So we have for the critically damped circuit, at I naught, we have something that says our final behavior, IL at time is equal to infinity. Okay. And then plus say plus the coefficient b. And I'm thinking, I guess I should write this one down. Don't forget, for the critically damped, you have something that says a times t to the r, I guess this would be alpha, the alpha t plus b e to the alpha t. Okay. So for the critically damped circuit, here we go. And we've already determined that our I naught should be 120 milliamps. Okay. That was right here. Well, our final, I'm going to actually look here at our final circuit after we did all those combinations. And you see what's going to be the final current through the capacitor or the inductor. Yeah, at infinity, the capacitor is fully charged, the inductor is fully charged, and so the inductor acts like a wire. Yeah, so this is going to get the full 100 milliamps. Okay. And so we see that at the end of the day, right, B is going to just simply be, I'll put, for sake of not messing up my units, I'll just put the amps here. And so that's amps, not this A coefficient. Sweet. Well, what do we have for our second condition? The time derivative of the current. And so handy dandy chart tells us that this should just simply be equal to A minus alpha times the value of B. So we go back and look and we said, hey, the time derivative is 0. So I should get that A is equal to alpha 10 to the 4th, B, which was equal to 0.020. And so I get that A is equal to 200. Should probably be able to do that in my head. And we're done. Right? Oh. Okay, it's gone forever. Okay, we'll rewrite it. And we're done. So what do we have at the end of the day? Our current running through the inductor as a function of time is equal to 200 TE to the negative 10,000 T plus 0.02 e to the negative 10 to the 4th T, and then plus our terminal behavior, 100 milliamps, excuse me, 1/10 of an amp. Look at that, right? The first time we did an example problem, it took us an hour. Now we've done 3 in an hour. Okay, I think that's enough examples for right now. I'll leave you to it. Keep hacking away at those problems. Don't leave them until Monday night. And yeah, we'll keep going. So, hey, thanks for your attention. I'll see you next time.